We're building these digital brains. We call them AI agents, and they can do incredible things. Write code, create art, plan our vacations. But there's a secret, a really dark secret right at the heart of this whole revolution. These brilliant assistants, these tireless workers, they can be profoundly, confidently, and sometimes catastrophically wrong. And here's the thing, they lie. I don't mean maliciously, but with this kind of digital madness. Today we're popping the hood to find out why, and to show you the secret engineering patches that bring some serious order to all this chaos.
I mean, just look at this. This is a perfect example. You ask an early AI agent for the factorial of a negative number, which, by the way, is a mathematical impossibility. And you don't just get an error message. Oh no, you get this. A hallucination. It just makes up an answer, and then get this, it comments on the temperature. A very cold number indeed. What does that even mean? This isn't just a simple mistake. This is a system that fundamentally does not get reality. This is the chaos we're talking about. An intelligence that can build nonsense on top of nonsense and sound completely sure of itself the whole time.
So here's the deal. We can't just build bigger and bigger models and hope this problem just magically disappears. It won't. We have to be smarter. We need a playbook, right? A set of engineering blueprints designed specifically to impose logic on these powerful but, well, unruly systems. And these blueprints are called Agentic Design Patterns. They're the secret patches that finally tame the wildness of large language models.
Okay, our first patch. This one is all about avoiding overload. If you give a human a giant, super complex task, what do? They break it down into smaller steps. Well, we need to teach the AI to do the exact same thing. Just think of it like an assembly line. You don't ask one person to build an entire car from scratch. You give each person one specific job to do, one right after the other.
See, instead of one giant messy prompt like, hey, read this entire 100-page report and write me a marketing email, we give the AI a sequence of smaller, focused roles. First up, act as a market analyst and just give me the summary. Done. Now, take that summary and become a trend analyst. All I want are the key trends. Perfect. And finally, you're now an expert writer. Draft an email using only those trends we just found. Every step is simple, it's focused, and the output from one becomes the clean, easy-to-use input for the next. It's a chain of logic that makes it way, way less likely for the AI to just wander off into la-la land.
Okay, so this whole assembly line idea, it's got a proper name, prompt chaining. The source material defines it as a method that breaks down one big, complex request into a series of simpler, connected prompts. What this does is it creates a modular workflow, which basically lowers the cognitive load on the model at each step. The result? A dramatic increase in accuracy.
So the assembly line works perfectly for a straight shot, right? A, then B, then C. But what happens when there's a fork in the road? What if a task could go in a bunch of different directions depending on what the user asks? Well, then you don't need an assembly line worker. You need a traffic cop. Someone to look at what's coming in and point it to exactly the right specialist. Think about any customer service bot you've ever used. When your question comes in, the AI's first and only job is to figure out what you want, your intent. Are you asking about an order? Okay, route them to the agent that talks to the order database. Need product info? Ship that request over to the product catalog specialist. Is the request just a jumbled mess? Send it to the one agent whose only job is to ask for clarification. It's not about doing all the work at once, it's about brilliantly directing the traffic. And that pattern, the traffic cop, we call that routing. It's a control mechanism that lets an agent actually change its path based on the input. So instead of just blindly following a single fixed track, the agent uses conditional logic, if this, then that, to decide which tool or which other agent to use next. This is how agents start to make real decisions.
Okay, so we've made our agent focused with chaining, and we've made it smart with routing. But what about making it fast? Some jobs, they require grabbing information from a ton of different places, and doing that one by one is just painfully slow. We've got to teach the agent to multitask. Let's take a travel agent. When you ask it to plan a trip, you don't want it to check flights, then wait, then check hotels, then wait again. No way. You want it blasting out all those requests at the exact same time. It should be searching for flights, hotels, and local events all concurrently. By running these independent tasks in parallel, it gets a complete picture of everything and gives you a full plan so much faster. And yep, you guessed it, this has a name too.
It's called parallelization. It's simply the pattern of executing multiple independent tasks or tool calls at the same time. The benefit here is obvious: a massive gain in speed and efficiency, especially for these complex jobs that have to gather and synthesize information from a whole bunch of different sources.
Okay, chaining, routing, parallelization, these are all awesome, critical patches, but they only fix how the AI thinks. They don't solve its biggest, most fundamental problem. An LLM is a brain in a jar. It's totally disconnected from the real world, trapped with knowledge that just stops cold the day its training data was collected. It can't check today's weather, it can't look up a live stock price, it can't even use a simple calculator. This next patch, this is the one. This is the real game changer. It's the moment we stop just fixing the AI's thinking and we give it hands. We give it a way to break out of that virtual box and actually act on the world around it.
This pattern is called tool use. It is the bridge connecting the LLM's brain to the outside world. It lets the model call external APIs, query live databases, or access online services. Now, the core technical engine that makes all this possible is something known as function calling. It's actually pretty straightforward. We basically give the model a list of functions or tools it can use, and it learns to figure out when and how to call them to get the real-time information it needs.
And this isn't just some high-level theory. You can see the code right here. And don't worry if you're not a programmer. All this little snippet does is define a tool called generate image. By giving the AI access to this function, a developer is essentially handing it a brand new skill. So now, when a user asks for a picture of something, the AI knows, hey, I can't just dream one up. I have to call this specific tool to do the real work for me.
And that is how you solve the problem from the beginning of our story. That is how we stop the lies. Instead of trying to do impossible math in its head and hallucinating an answer, the agent now learns to recognize, oh, this is a math problem. I need a calculator. It calls the calculator tool, the tool returns a proper error message, and now the agent can give you a correct, fact-based response. This is how a cheap AI agent learns to use a search engine to check its facts or a stock API to get real-time prices. It learns to act instead of just invent.
So, great, we've done it. We've patched the single agent, we've made it logical, decisive, efficient, and connected it to reality. It's an incredibly powerful tool. But in solving the chaos inside one agent, we've just stumbled upon a much, much bigger challenge. We've built a brilliant specialist, but the world is absolutely filled with problems that are way too big for any single specialist to solve.
Look at it this way. A single agent, even a perfectly designed one, is like a highly skilled specialist. It's amazing at its one job. But what about a real-world problem, like planning an entire company retreat? That needs a budget expert, a travel coordinator, a survey analyst. It requires collaboration across different domains. Real-world problems are messy. They're ambiguous. They change on you. They don't need a single worker. They need a team.
Which leaves us with one massive question, doesn't it? These 4 patterns are absolutely essential patches for fixing the flaws of a single agent. But what happens when the problems get too big for one agent to handle? How do we get these specialized AIs to collaborate, to form a team, and to tackle challenges that are far beyond the scope of any one of them? Well, that's the next frontier.